Welcome back. This is lesson 14 of our semester-long videos on basic circuit analysis. Today we're looking at the step response of RC and RL circuits. Now, this lesson is going to get a little mathy, especially at the beginning. In fact, we're not even going to look at circuits at the beginning of this lesson, just some math functions. And later we will tie in the circuit part of this. So first of all, I just want to cover what this part of the title means, the step response, the step in particular. So a function that you have not seen in your math classes is called the unit step function. The unit step function. And the reason you have not seen the unit step function in your math courses is that it's what we call a singular function, meaning it's not analytic, it does not have a well-defined derivative, and the function itself is not well-defined. So you're used to seeing things like f of x, okay? This f would be a function, and x is the independent variable. You tell me what an x is, then I'll evaluate the function at that x. All right, well, for circuits, we're worried about time. You can go back to the last video and understand why we're worried about time. So our independent variable is not x, it's going to be time. F of t, right, would be some function of time. And the unit step function, we don't use the symbol f for any old function. We use the symbol u, meaning a particular function, the unit step function. So the unit step function, u of t. And sometimes this function, instead of saying the unit step function, we just call this a step, or a unit step. All right, so the unit step is defined, well, it actually depends on the reference. But your book defines the unit step as 1 when time is greater than 0 and 0 when time is less than 0. Alright, so think about that for a second. And does something stand out to you at all about this definition? Well, maybe you can ask the question, what about t equals 0, right? What's u of 0? What's the unit step function at 0? Well, your book leaves it undefined. Undefined. Some references will say the unit step at 0 is 1. Some references will say the unit step at 0 is 0. And some references even say the unit step at 0 is 1/2. Okay, we're going to stick with your book, and we're just going to leave that undefined. In fact, it really doesn't matter what the unit step function is at that exact particular moment in time. This matters up here. Positive time, negative time. So let's make a plot of it. Right. So here's the unit step. I'll give some labels to our axes. U of t. Here's t. Right. So what does such a function look like? Well, it's 0 for time less than 0. So if here's the origin, right, t equals 0, then our unit step function is 0 right here. For all values of time less than 0, and for all values of time greater than 0, the unit step function is 1. there's our function. All right, and we can do certain transformations to this function, transformations that you should have seen in high school algebra, such as what would u of t minus 1 look like? I'll do it in blue. Let's draw it in blue. Okay, so here's u of t. What would u of t minus 1 look like? So this is notation for subtracting 1 from the independent variable. All right, well, if it's not obvious to you what this looks like, you can plug in some values of time, t. For example, let's let t equal 0. Okay, at t equals 0, this function, u of t minus 1, is equal to u of minus 1. Well, what's u of minus 1? U of minus 1 is, again, defined as 0. For when the time is negative, it's defined as 0. So now we have the point t equals 0, 0. So we've got this guy right there. Notice, if I plug in a value t equals 1, well, here's where I have my discontinuity, because when t equals 1, this function, u of t minus 1, is equal to u of 0. But we don't know what u of 0 is. So, but the point here is that at 1 unit of time, this is where the jump occurs. Okay, in fact, if you plugged in t equals 2 to this function, this would be u of 1. So u of 1, this is positive time, so that's 1. So we've got the point 2, 1. So if this is 2 over here, we've got the point 2, 1. And in fact, everything more than 2, and actually everything more than 1, you're going to get positive time there, and this function is going to be equal to 1. Let me draw that a little bit better. Right. So here's our function. This is 1, and this is 0 down here. So what does subtracting 1 from the independent variable do to a function? Well, it delays it in time, right? In this case, we subtracted 1 from the independent variable, and it delayed it by 1 unit of time, right? Because here's the discontinuity at 0. Now the discontinuity occurs later in time at 1 unit, 1 second, or 1 millisecond, or whatever the unit of time there is. So you can imagine what u of, I'll do this in green, what u of t plus 1 would look like. Actually, if you want to think about that, or if you want to try plugging in some values of time, go for it. And pause the video. But what happens is that this is essentially this thing, except the delay, if you want to call it that, is not 1, it's minus 1. So the shift is to the left by 1 unit. So if we plugged in values of time, we would see the discontinuity happens here at 1 unit. And so we'd have 1 and 0 here. Okay, so these are shifting the independent variable around. Now, let us try to express a square pulse in terms of the unit step. So let's say we have a function of time, f of t, and our function of time looks like this. So, and we'll call this 10. So this is a height of 10, and we'll let this be 2. So this is going to be 2, and this is going to be 5. Right? And the question is to write f of t in terms of the unit step. Write f of t in terms of the unit step. Alright, well, this square pulse has two discontinuities. One at t equals 2 units, and one at t equals 5 units. So the one at t equals 2 units, we can write as, do it in red, u of t minus 2, right? If we take the unit step and we subtract 2 from the independent variable, that shifts it, like this blue wave, that shifts it to the right by, in this case, 2. So that's going to make the discontinuity at 2. But you see, this guy, the original function f of t, jumps by 10 units. Okay, the unit step, by definition, only jumps by 1 unit. So you might think we would scale it by 10. Right? And in fact, that's not quite correct yet, but it's a good start. And we'll come back and we'll modify that a little bit. Right? So this wave right now is 0, 0, 0, 0, 0, 0, and then at 2 jumps to 10, and it goes on to 10 forever. Okay? So now we need to account for this second discontinuity. Well, here the unit step comes down, right? It comes back down to 0. So now let's modify this guy. We want to subtract now, because the discontinuity is down. We're going to subtract a unit step, and we want to subtract 10 units. 10 times the unit step, and the discontinuity happens at 5. So we're going to say t minus 5. And we suspect that this is our function. This is the answer. That's our guess. And let's plug in some values of t to see if that's correct. Okay? So, for example, let's let t equal 0. Okay, at t equals 0, we have 10 u of minus 2 minus 10 u of minus 5. Okay, but the unit step of a negative number is defined as 0. So this is 0, this is 0. So our function at t equals 0 is equal to 0. So that's this point here. Good. That lies on, I guess I should show this part. That lies on our function. That's good. All right? In fact, any value of time less than 2 is going to give us a negative number in this term, a negative argument, right? A negative argument. It's going to give us a negative argument here if it's less than 2, and a negative argument here if t is less than 2. And 2 negative arguments, the unit step is 0 here and 0 here. So anything less than 2 for t is going to give us 0 in our function. So that's good. That's this whole piece here. Now let's plug in a value of t in this window here. Let's try 3. We have 10 u of 1 minus 10 u of 10 times u of negative 2. Okay, well, this is a positive argument to the unit step. So u of 1, right, is 1. So this is 10. U of minus 2 is 0. So this is 10. That's good. And that's this point right here. It lies on our function. In fact, any value of t between 2 and 5 is going to make this thing positive, this argument positive, and this argument negative. And that makes this term 10 and this term 0. So we have 10. So anything between 2 and 5 makes our function 10. That's good. That's this part. Now let's test out this part, the third section here. Let's plug in, for example, t equals 6. When I do that, I've got 10 times the unit step of 4 minus 10 times the unit step of 1. So these arguments are both positive, so the unit step is 1 there. So this is 10 times 1 minus 10 times 1. So it's 10 minus 10, that's 0. So that's good. That lies on our function. That's right here, about. And in fact, any argument, any value of t that I plug in larger than 5 makes this argument positive and this argument positive. And so this unit step is 1 and this unit step is 1 and the function is 0. That's this whole piece there. So yes, this in the box is the correct representation of this square wave. Let's try one more, and I'm going to erase what we have here. All right, let's say we have another square wave. Okay, but it looks like this. So it's 0 here, then it's 10 here, 10 units, whatever the units are. Then it drops to minus 10, and it comes back up to 0. Right. Here's our function. We're going to call this f of t. And the directions are, again, write f of t in terms of the unit step function. All right. So, or let's give the time axis some labels here. Let's make this 2 and 4. So we have a jump f of t equals, we have a jump at 0. Okay, so that's an unshifted unit step, right? A jump at 0, but it jumps from 0 to 10. So we'll start with just 10 times the unit step. So we've got that. So that, if just that piece would be 0, 0, 0, then jump to 10, and it would be 10 forever. But at 2, okay, I have to go back down to negative 10. So that's a jump of, in total, 20. And it's a jump downward. So I'm going to subtract 20 times the unit step shifted by 2 units. So now I stay at that level until 4 units of time, when I jump positively by 10 to get back to 0. So I'm going to add 10 unit step shifted by 4 units, because that's where I want that discontinuity to be. And then I have no more discontinuities, so I suspect that is my answer. All right, let's just test it out. Let's pick a value, let's say t equals -1. All right, well, f, according to our equation, f of -1 would be 10 times the unit step evaluated at -1 minus 20 times the unit step evaluated at -3 plus 10 times the unit step evaluated at -5. Right? So these are all negative input arguments into the unit step. So these are all 0. 0. In fact, anything less than 0, any argument of any value of t less than 0 is going to give me a negative input argument here, a negative input argument here, and a negative input argument here, and so the whole thing is 0. That's this piece. Now let's try this piece. So I'll conveniently plug in t equals 1. F of 1, according to our answer, is 10 times the unit step of 1, minus 20 times the unit step evaluated at -1, plus 10 times the unit step evaluated at -3. All right, these two, the last two input arguments to the unit step are negative, so they're 0. And in fact, I just get 10 times the unit step of 1, and the unit step of 1 is 1. So this is 10. That's good. That's this piece up here. All right, so you can continue on like that, and you should test out this piece. You can plug in t equals 3, and you'll see that this is correct. And you should test out this piece. You'll see you can plug in 5, 6, 7, whatever. You can plug in fractions and decimals as well. Okay, they don't have to be integers. Plug in whatever value of time you like, and you will see that you get 0 here. So this is the correct answer. All right, well, let's start to bring circuits into this a little bit now. And I want to go back to the unit step itself. Unshifted, unscaled unit step. So the unit step was this, right? 1, 0. So now suppose I had a circuit, and we'll say it's got a source, and we'll say it's a voltage source. We'll say of 1 volt. 1 volt voltage source, and there's a switch here, right? So think about it. You switch on your power strip or something like that. So voltage sources usually have a switch to them. So here's a switch, and I'll draw the terminals here, and these terminals are connected to something, some resistive network, capacitive network, whatever. It's connected to something there. And let's say we switch in the voltage source at t equals 0. So our reference point is t equals 0, and we're going to switch it in, right? So at this point right here, without the voltage source, we have 0 volts, okay, because it hasn't been switched in. And then at time t equals 0, we switch it in, and now we have 1 volt there. So think about that for a second. We had 0 volts, and then at our reference point in time, t equals 0, now we have 1 volt. Well, what does that remind you of? Yeah, the unit step. So the voltage here, call it V of t, right, we can say is actually just the unit step. So I can replace the switch and the voltage source simply with a voltage source and say that the voltage here is U of t. U of t now. Right, the switch is gone because the switch is inherent to the unit step. Right? Here's the switch in the unit step. You say, okay, well, what if I didn't have exactly 1 volt? Right? What if I had a 9-volt battery there? That's no longer the unit step, right? We have 0 volts, and then we switch that in, and we have 9 volts. Okay, well, that's 9 times the unit step, actually, right? Because now we have a jump of positive 9 units. So that's precisely 9 times the unit step. So these two pictures here, picture A, picture B, those are equivalent. The switch, again, is built into the unit step itself. All right, finally, you might say, well, what if the switch is not happening at my reference point in time? What if it's happening, after? Maybe it's a delayed switch. Well, let's say we have 9 volts, right? And we are switching in at maybe 1 unit of time. Maybe that's a second, 1 second. We wait. Well, what would that be? Think about it. That's a delay in time, right? So our source now is 9 unit step of t minus 1. Right? Because this thing, again, subtracting 1 from the input argument, shifts the unit step over by 1 unit to the right. Delays it. So these pictures here, C and D, picture C is the same as picture D. So the unit step then is a convenient way of representing this idea of a voltage source being switched into a circuit. And I do want to point out that this also works for current sources as well. When current sources are switched in and out of circuits, we can use the unit step. All right. I'm going to erase this. And now let us consider the following circuit. Let's say we have a voltage source, Vs, in series with a resistor, and that combination there is switched in at time t equals 0. Call this voltage V. And here's the capacitor. V. Alright, and there's of course a current going through this. This is I, resistor R, excuse me. There's a current going through this loop when the voltage source is switched in, and we'll call that current. That current's I. Right? And let us also suppose the capacitor is charged and that charge then gives rise to its initial voltage V0. Okay, so the capacitor is, so V0 is the initial voltage, okay, on the capacitor, or across the capacitor, might be a better word. All right, this circuit is equivalent to this model Vs U of t. Right, here's V. Okay, so you can use whichever one you prefer, but this is the new idea here, that this switch, the voltage source, is being switched in, and we can model that with the unit step. Right. So, and I also want to remind you that V0 is the initial voltage on the capacitor, so that makes V of 0 minus. Okay, the voltage right before the switch was V0, and that must be the voltage of the capacitor right after the switch, because the capacitor's voltage cannot change instantaneously. All right, well, we can do, I'm going to look at this picture here, down here, second picture. And we can do a Kirchhoff's voltage law around this loop. Or actually, let's do a Kirchhoff's current law. So at this node here, let's do Kirchhoff's current law. So the current coming in here must be the current coming out there. All right, so the current coming in, well, we can use Ohm's law. That's Vs U of t minus the capacitor voltage divided by the resistance equals the current leaving, so that goes through the capacitor. So this is C dV dt, C dV dt. All right, and if I rearrange that a little bit, okay, then I get dV dt plus V over RC equals Vs over RC U of t. You see that R times C, that product is coming up. Remember, that's tau, the circuit time constant. Now, the unit step is 1 for time greater than 0. So, for t greater than 0, okay, we have dV dt plus V over RC equals Vs over RC. And we can rearrange a little bit and separate the variables to get dV over V minus Vs equals dt over RC. Okay, so we're going to solve this differential equation by using the method of separation of variables. Everything with a V is on the left, everything with a T is on the right. So we can integrate, okay, and so we're going to integrate the left. 1 over V minus Vs dV is the natural log of V minus Vs. Okay, and we're going to integrate this from our initial condition, right, V0 to the voltage at the time right now equals the integral of this guy, right? Oh, I lost the negative sign here. This should be negative, because when I bring it over to the right, I need a negative there. So when I integrate this, there's no t there, so this is just negative t over RC, and I integrate, time goes from 0 to t, the current time. The initial, right, the switch happened at t equals 0, and then whatever time we're interested in now, we integrate that t. So when I do that, when I plug in the bounds, I get the natural log of v of t minus vs minus the natural log of v0 minus vs equals negative t over rc. And if I rearrange a little bit and take the exponential of both sides, I get v of t equals vs plus v0 minus vs times e to the negative t and over rc, right? That's tau, remember. And again, this is for t greater than 0. So I'll just write that again, t greater than 0. Right, so here's our solution. And for t less than 0, that's when the voltage source has not been switched in yet. So the voltage across the capacitor is simply this initial voltage. It's really not a function of time, it's a constant. So now we can put these two things together, these two pieces, right? T less than 0, t greater than 0, piecewise. So we can say v of t equals v0 time less than 0 vs plus v0 minus vs e to the negative t over tau for t greater than 0. Okay, so here's the total response for all of time. And I use that word response, okay, because this is the response of the capacitor to the step, the voltage being switched in, hence the step response. And this is an RC circuit, so this is the step response of an RC circuit. There it is. Now, I want to focus on after the switch. Okay, after the switch, if I distribute the e to the negative t over rc in, right, I'm going to erase some of this here. I'm going to erase this. Let me distribute that in. So again, for t greater than 0, if I distribute that in, you'll see I've got a vs plus v0 e to the negative t over tau, and then a minus vs e to the negative t over tau. And if I group the vs's together, okay, then I find that the capacitor voltage is Vs times 1 minus e to the negative t over tau plus V0 e to the negative t over tau. Right? And I want to point out to you that, well, this should look familiar. This term should look familiar here. Now, what is this term? Well, this was the voltage across the capacitor in the source-free circuit. So let me draw that just to refresh your memory. Here, right? We said suppose that the capacitor was charged with a voltage V0 initially, and then we just let this thing run its course, and the capacitor voltage dies out to 0 according to this, underlined in orange. We call that the natural response. That's the capacitor's natural response. Okay, so what is the other two terms then? Okay. This thing here. All right, this is called the forced response. The forced response. This is this is what the orange is what the capacitor wants to do naturally, okay, like this here in the source-free circuit. The forced response is what the voltage source Vs is forcing the capacitor to do, right? And so the total voltage is the forced response plus the natural response. And this is a sneaky application of superposition, believe it or not. I say sneaky because if you go back to the superposition video, we used superposition when there were more than one source, right? Two sources. So where are the two sources here? Well, we said that the capacitor, when it's initially charged, kind of is effectively a source. It's an energy source. It makes a current and a voltage and so forth until it dies down. Okay? So when the voltage source in this original circuit is switched in, until the capacitor dies down, we effectively have two sources there, the capacitor and the voltage source. So it's not a surprise then, because we know superposition, that the capacitor voltage V is a sum of the capacitor voltage, the natural response, and this other term, the forced response. All right. Well, that's a lot to take in there, and we don't want to have to go through the calculus for every circuit and solve the differential equation, right? So I'm going to give you more of a systematic approach, or a shortcut to finding the total response, right? So when we take the forced response plus the natural response, that's the total response. Okay, so if we have an RC circuit and we want to know what the step response is, right? Well, that's going to be the voltage across the capacitor at infinity, and I'll explain that in a second, plus the voltage of the capacitor right after the switch minus the voltage of the capacitor at infinity times e to the negative t over tau. The voltage across the capacitor at infinity, so this means after the switch, let it run its course, meaning wait several time constants, 5, 6, 7 time constants, to where the capacitor is effectively an open circuit. So in this case, here's Vs. Okay, we're at time equals infinity, so the switch is closed, but the capacitor has reached its DC steady state. So what's this voltage here? V. Well, there's no current that flows through the resistor, so there's no voltage drop across that resistor. So this voltage is Vs. And again, this is V of infinity, right after the switch, and we've waited a long time for the natural response to die down. Vs. Now, the voltage at 0 plus, we already said that's the initial voltage here, V0. Right? So let's plug everything into our equation here in black box, the black box, see what we get. Right? So we get V of infinity, that's Vs, plus V0 minus Vs e to the negative t over tau. And so that is exactly this here. That's our answer. Okay, so your systematic approach here is to first find V of infinity. So that means after the switch. Right? After the switch and at DC. We've waited a long time and the circuit settles down and nothing is changing anymore, and so it's now at DC. So find V of infinity. Also, and you can do these in any order really, find the voltage across the capacitor right after the switch. Third, find the circuit time constant, tau. Once you have these three things, you can get this equation perfectly. Alright, so let's look at an example. Suppose we have a 24 volt source here and a 3 kilo ohm resistor, a 5 kilo ohm resistor, and a switch that goes from A to B at t equals 0. And here is our capacitor of 0.5 millifarads. Right? So here's our circuit. So we're essentially switching between now two voltage sources, 24 volts, 30 volts, and we want to find, well, first we'll say that the capacitor is initially uncharged. So let's say the capacitor is initially uncharged. Find V for all time. Actually, let me back up. We can't say that it's initially uncharged because the current state of the switch, there is some energy there from the 24 volt source. So we're not going to say the capacitor is initially uncharged. My mistake there. So we are going to say find V for all time. And here's V. Okay. So again, I want to clarify that it is charged before the switch. Because of the 24 volt source, there's going to be a voltage across the switch there. And then when we switch it to position B, there will be another voltage there. Alright, so our systematic way was to first find V of infinity. Right? So that was the voltage after the switch and after we wait a long time. So after the switch, our circuit, our capacitor, is an open circuit after we wait a long time, and we're in position B. Like this. So what is that voltage there? Well, again, there's no drop across the 4K resistor, so all the 30 volts makes it to the capacitor. So V of infinity is 30 volts. Now, we can also find the voltage across the capacitor right after the switch. Alright, so right after the switch, the voltage is the same as right before the switch, because in a capacitor the voltage cannot change instantaneously. So right before the switch, we assume that this circuit was built a long time ago and all the transients have died down and the circuit is at its steady state. Okay, so right before the switch, the circuit is at its steady state And the capacitor is modeled. It's effectively an open circuit. Okay, so this is before the switch, and it was built a long time ago, and the capacitor is an open circuit. So the voltage here is the voltage across the 5 kilo ohm resistor. So we can get that with voltage division quickly. Right, so this is 24 volts times 5k ohms divided by 5 kilo ohms plus 3 kilo ohms. So this fraction is 5/8. 5/8 times 24 is 15 volts. Right, so again, that's the voltage across the capacitor right before the switch. Then that voltage must be right after the switch as well, because the voltage across the capacitor cannot change abruptly. 3, let's get the time constant. So the time constant is how the circuit is changing after the switch, right? So we need to consider after the switch again. So here's our capacitor, 0.5 millifarads, 4 kilo ohms, and the 30 volts. Right, so how much resistance does the capacitor see? So the equivalent resistance looking into the capacitor, remember we short out the voltage source, and we see only the 4 kilo ohm resistor. So the tau here, the time constant, is 0.5 times 10 to the minus third farads times 4 times 10 to the third ohms, RC. I guess I wrote it as CR. Sorry about that. So the 10 to the third and the 10 to the minus third cancel, and we get 0.5 times 4, which is 2 seconds. All right, so the voltage for time greater than 0 is V of t equals. Now we've got, remember that equation there, V of infinity, 30 volts, plus V at the switch, so that was 15 volts, plus the 30 volts, excuse me, minus the 30 volts, times e to the negative t over tau, which is 2 seconds. All right, so V of t is 30 volts minus 15 volts e to the negative t over 2. And again, that was at t greater than 0. For t less than 0, we saw that the voltage was 15. So V of t is just a constant 15 volts. So we can put all those pieces together and say, for any time, capacitor voltage, well, it was 15, t less than 0, and 30 volts minus 15 volts, e to the negative t over 2 for time greater than 0. And that is the answer. Find V for all time. All right, let's look at another example. So here we'll have a voltage source, and we'll say this is 30 U of t volts. 10 ohms. $20 ohms. 1/4 farad. And call this 10 u of t. No, excuse me. Let's have a switch here opened at t equals 0, and this will be 10 volts. Right? And we'll say we're looking for the capacitor voltage, V, and let's throw another circuit variable in here. Let's throw I in there as well, this current through the 10 ohm resistor. So this voltage is going to be changing with time. Hopefully you understand that by now. So what about this current? So we'll get there in a second. So find V and I for all time. Okay. Well, right now, all you know is how to find V. So let's find V first, and then we'll get to I. So we'll find V in that systematic way. So let's find first V of infinity. All right, so if we consider this experiment or this circuit in a long time from now, well, we've got 30 volts switched in because the unit step is 1 for positive time. So this is 30 volts here, and for positive time this is open. So our circuit at V of infinity looks like this: 30 volts, 10 ohms, 20 ohms. If we wait a long time, the capacitor is effectively an open circuit. So we want this voltage here. This is V of infinity. All right, again, we can get this from voltage division quickly. This is 30 volts times 20 ohms over 20 ohms plus 10 ohms. So that fraction is 2/3. 2/3 of 30 volts is 20 volts. Okay, step 1 done. Step 2, let's consider the voltage right before the switch. Right? Well, right before the switch, at negative time, the unit step is 0. 0, right? So we've got this circuit. What does 0 volts look like? 0 volts is a short circuit. And assuming the circuit was built a long time ago, capacitor is open. And see, at negative time, the switch is closed here. So here's our circuit. And this is V0 minus. Right? So how many volts do we have across the capacitor? Well, 10 volts. The capacitor is connected directly to the 10 volt source. So V0 minus is the same as V0 plus right after the switch. We start with 10 volts. Step 3 is find the time constant, right, tau. So again, it's important to emphasize here, the time constant is after t equals 0. We're interested in what's happening after all of this is going on, how the transients die away, and so forth. So for positive time, again, we've got 30 volts over here. So that's this circuit, 30 volts. This middle circuit here, 30 volts, right? 20 ohms. But the capacitor is not necessarily a short, or excuse me, not an open. So let me redraw the circuit actually. So we've got 30 volts right after the switch. Okay, we've got 20 ohms. We've got the capacitor, 1/4 farads, and the voltage source on the right is switched out after t equals 0. So the question is then, tau is of course R times C. C is obvious, it's 1/4 farad. What is R here? Right, well, we want to know what is the equivalent resistance seen at the capacitor terminals. So we want to remove the capacitor and look inside the terminals and turn off the voltage source, and that makes the 10 in parallel with the 20. So we have 10 times 20 over 10 plus 20. This is the equivalent resistance, right, ohms. So that's 200 over 30 ohms, 20/3 ohms. So the time constant then is 20/3 ohms times 1/4 farads. So that is 5/3 seconds. Alright, so in total then we have the capacitor voltage is, right before the switch it was at 10 volts. T less than 0. So for all time less than 0, we've got 10 volts sitting at the capacitor voltage. But then at t equals 0, that's when the action is happening here. That's when this switch is open. That's when this thing switches on the left. So at that point now, we have, again, we're going to make use of that equation, systematic equation here, V of infinity, 20 volts, plus V of 0 plus is 10 volts, minus V of infinity, 20 volts. So we have a minus 10 volts there. So let me get rid of the bracket. Minus 10 volts, e to the negative t over tau over 5/3 for t greater than 0. So that's the voltage. What about the current? Right? What about the current? So for the current, so we have the voltage for all time. That's V. So that's the voltage from this node to this node. Okay? Well, we can still use Ohm's law. Right? Let's consider this to be our reference. So if this is 0 volts, then this up top is V of t, right, which we have. So the current I is simply 30 U of t minus V of t over 10 ohms. Right, that's Ohm's law. The voltage from the left minus the voltage on the right divided by the resistance. Alright, so for time less than 0, I equals, well, the unit step is 0, and so we have minus, and then this thing is 10 volts, so we have minus 10 volts over 10 ohms, so the current is minus 1 amp. For t greater than 0, the unit step is 1, so we have 30 volts minus this thing. So that's minus 20 volts plus 10 volts e to the negative, and I'll write this as 3t over 5 divided by 10 ohms. So this is 10 volts over 10 ohms, which is 1 amp. Then we have another 10 volts over 10 ohms plus 1 amp e to the negative 3t over 5. Alright, so putting it all together, I equals negative 1 amp for time less than 0, and if we factor out the 1 amp, 1 plus e to the negative 3t over 5 for time greater than 0. Here's our solution. Again, if you need, pause the video. Pause the video, work it out yourself. Right? But we are moving on now to the RL circuit. And we're not going to go through the RL circuit with as much detail as we did to the RC because it's very similar. Well, recall with an inductor, the roles of voltage and current switch from that of a capacitor. So we're going to avoid going through much of the same analysis for RL circuits, and we're just going to jump to the conclusion, and it should not surprise you based on what you know of inductors and capacitors. Our methodology for finding the current in an inductor is to first find the current through the inductor at infinity. Okay, this is after the switch. After the switch and at DC. Right? And remember, the inductor is a short circuit at DC. Find the current through the inductor right after the switch. Okay. And to do that, note that that is the current right before the switch. So essentially this is right before the switch. And if the circuit's been sitting around for a while before the switch, then it too is at DC. Then, of course, find tau. And just to refresh your memory, that is L over R for an LR circuit or an RL circuit. And then the equation that we need here is the current through the inductor, I of t, is I at infinity plus I at 0 plus minus I at infinity e to the negative t over tau amps, right? So this is very similar to what we just did with the capacitor. So let's now look at one example, right? And I'm going to actually keep the methodology up here, and I'm going to draw the circuit down here. So let's say we have a 10-volt source and a 2 ohm resistor, a 3 ohm resistor, and a switch here that is opened at t equals 0. And here's our inductor of 1/3 Henry. The question is, we're going to find the current through the inductor, but also we're going to find the voltage across this resistor. Okay, oh, how are we going to do that? We have no methodology to find that voltage. Well, we have the switch and so forth, so we do have the methodology for finding the current. Let's start there and then discuss the voltage across the resistor. Okay, so again, we're going to find I and V for all time. Okay, so right before the switch, right, the switch is closed. So if the switch is closed, this resistor, the 3 ohm resistor, is shorted out. Okay, so effectively what we have here is this, right? And if the switch has been closed for a really long time before being opened, then the circuit is at its DC steady state, which means that the inductor is a short. So here's the current, right? and this is I 0 minus, right? So this is right before the switch, and assuming that switch has been closed for a really long time. The circuit was built a long time ago, and of course we mean long time as in 5 time constants ago. Alright, so we can find that current very easily, actually. That's from Ohm's law, 10 volts divided by 2 ohms, 5 amps. Alright, that's right before the switch, and because the current can't change abruptly through an inductor, that is also the current right after the switch. Right? So that's it. We actually did step 2 there first. You can interchange any of these 3, really. All right, now let's go find the current after we wait a long time. So now the switch is open. All right, switch is open, and we wait a long time. So we open the switch, we wait 5 time constants or more, and so notice that 3 ohm resistor is no longer shorted out. Okay, because again the switch is open. And if we wait a long time, again, the inductor reaches its steady state equivalent, and so it's modeled as a short. So we're looking for this current, and this is I at infinity now. So we have, again, this is very easily solved. This is 10 volts over, and then these are in series, 5 ohms. So this is 2 amps. So you see what's happening here in this circuit. The inductor is going from 5 amps to 2 amps. Right? It was at 5 amps before the switch. Then we pull that switch, and eventually it goes to 2 amps. So the question is, well, what is the transition that it makes in going from 5 amps to 2 amps? It does not happen instantaneously or abruptly. So step 3, then, let's find the time constant, circuit time constant. And remember, this is after the switch now. We want to know, how does it go from 5 amps to 2 amps? So after the switch, again, our circuit looks like this, right? As the circuit is running its course, right? We have this guy, and we ask ourselves, how much resistance does the inductor see, right? So, in other words, what is the equivalent resistance at the inductor terminals, right? We're looking for this resistance here, this equivalent resistance. And so you turn off the voltage source, and we have 3 ohms in series with 2 ohms, so we know that that's 5 ohms. So the circuit time constant is L over R, so that's 1/3 Henry divided by 5 ohms. That's 1 over 15 seconds. Okay, so when I say that the circuit's built a long time ago, and when we wait a long time, we're really saying about 5 time constants. So in this case, that would be 1/3 seconds. That's what we mean by a long time, believe it or not. All right, so I'm up here in red, or in blue, or no, excuse me, in red. I'm going to write now the answer. So we're going to apply this boxed equation that for t greater than 0, I've got I of infinity, so that's 2 amps, right? Then I of 0 plus, which is 5, minus the 2 amps, so that's 3 amps. E to the negative t over tau. So over 1 over 15 makes 15 t, like that. All right, so again, that was when t is greater than 0. All right, what about when t is less than 0? Well, assuming the circuit was at its steady state, then we already found the current before the switch. It's 5 amps. 5 amps. So that's it. That's the current through the inductor for all time. Now, let's talk about that voltage across the resistor, right? I'll do this in blue. So we have no equation for the voltage across a resistor given this switching situation, okay? But we need to apply some logic here. We do know the current now, and after the switch, the current only had one way of coming from. That was through this 3 ohm resistor, right, after the switch. So we can use Ohm's law after the switch and say the voltage is I times 3 ohms. And here's I after the switch, right? So multiply this thing by 3 ohms. So we get 6 volts plus 9 volts e to the negative 15t. And again, that was for when time is greater than 0. Less than 0, so before the switch, that resistor was shorted out, so the voltage across it is 0. And that's it.